We define the degree of a field extension as the dimension of the larger field as a vector space over the smaller field. So the degree of an extension f k over f is the dimension of k over f. See, f is a subring of k, and therefore k becomes an f module. And in this case, f is a field, so k is a vector space over f. It makes perfect sense to talk about the dimension of k over f. And the notation is k colon f. So for example, the degree of c over r is 2, but the degree of r over q is infinity. So degrees can be infinite as well. Now, what about the extensions generated by an element? So let's consider the situation where we have a field extension k over f and we have an element alpha. So then we can ask, what is the degree of f alpha over f? It turns out that it is just the degree of pt, where pt is the irreducible polynomial of alpha over f. And the proof is very simple. It's just that we know already that f alpha is ft mod the ideal generated by pt. And this ft mod pt, if pt is a polynomial of degree d, then 1 t squared all the way up to t to the power d minus 1 form a basis of ft mod pt. So the dimension of f alpha over f must be d. The smallest non-trivial extensions are what are called quadratic extensions. So extensions of degree 2 are called quadratic extensions. That's because they come from quadratic polynomials. It's very easy to describe quadratic extensions, exactly what they are. So now suppose k over f is a quadratic extension. They take any element of k which is not in f. Okay, so alpha is in k minus f. Then we know that 1 comma alpha is a basis of k over f, just because it's a linearly independent set of size 2. And so what we know is that alpha squared must be a linear combination of 1 and alpha. So I can write alpha squared as p alpha plus c, but just for what is about to come, I'll write as minus b alpha minus c. Okay, it doesn't matter. But the point is now that let pt be the polynomial alpha square plus b alpha plus c. So then p of alpha is 0. So we can write down a polynomial, a quadratic polynomial, such that k is isomorphic to ft mod pt. and this is an isomorphism over F. Now we can simplify this situation further by trying to okay, so if we try to solve, so there are two roots of this polynomial. One of them is alpha and the other is something else. How are these roots given? So note that the roots of PT are minus b plus or minus square root of b squared minus 4c, and we need to divide by 2. So let's assume that f is not a field of characteristic 2. So that means that 1 plus 1 is not equal to 0 in f. So 2 is equal to 1 plus 1 is not equal to 0 in f. Okay, with that assumption we can divide by 2. So 2 is non-zero, so we can divide by 2, and so we get that these are the roots, and one of them is alpha. So there's anyway always a choice of square roots of b squared minus 4c. So let's just write, choose a square root in such a way that this is alpha. So let's say we have alpha equals, for an appropriate choice, so let's call this thing d, b squared minus 4c, and so this is minus b plus root d by 2 for an appropriate choice of root d. Let's call it delta. Okay, so what we have is that alpha is minus b plus delta by 2, and we can also write delta is 2 alpha plus b. So what these two identities mean is that q alpha is equal to q delta, because if a field contains alpha and not q, I guess what I want to say is f alpha and f delta. This is general, and this is because if a field contains alpha and it contains f, then it must contain 2 alpha plus b, because b is in f and 2 is in f, so 2 alpha plus b must be in that field. So that means that delta is in that field, so f delta is contained in f alpha. Conversely, if a field contains delta and it contains f, then it must contain minus b plus delta by 2, which is alpha. So f alpha is contained in f delta. So we have that f alpha is equal to f delta. So this field extension, this quadratic extension of degree 2, can be just written as it's the extension generated by the square root of some element d in K. So it's f adjoint delta, or we can write f adjoint square root d for some d. So every quadratic extension is of the form, well, if you're working inside a larger field, then it's of the form, it's generated by the square root of a single element in f. So for some d, this d is in f. For some d belonging to f. Here's a exercise for you. So suppose you have some field extension K over F, and not necessarily quadratic, and E and D belonging to F are two elements without square roots. So they belong to F which do not have square roots in F. So then you can talk about FE, and you can talk about FD. So then FE is isomorphic to FD over F. Show that D is equal to E. So what this is saying is that all the quadratic extensions of F inside K correspond to elements of F which are not square roots, which are not perfect squares in F itself. Now we'll talk about the degree of a tower of extensions. This is a very important result. So by a tower here, not a very tall tower in this case, of extensions, I mean three fields L containing K containing F. Okay, so you consider such a tower of three fields. And so then the question is, what is the relationship between the degree of L over F and the degree of L over K and the degree of K over F? And it turns out that the degree of L over F is precisely the product of the degree of L over K and the degree of K over F. This is not a very difficult theorem to prove. If you just think about it, you'll probably come up with a proof very similar to what I'm going to give here. So you can try pausing the video and trying to come up with the proof. Or you can watch a little bit and then try to finish the proof. So what we'll do is we will construct a basis of L over F from a basis of L over K and a basis of K over F. So suppose we have y1, y2, yn is a basis of L over K and x1. So these are all elements of L. x1, x2, xm is a basis of K over F. My claim is that you look at the set xi, yj, where I goes from 1 to m and j goes from 1 to n, then this is a basis of L over F. Okay, you can try to prove this as an exercise. Just pause the video and try to do it. If you can't do it, then watch. So we need to show two things. We need to show firstly that L is spanned by this set. So let's do that. So given alpha in L. Okay, so alpha is an element of L and we have a basis of L over K. So we can write alpha in terms of the y1, y2 and yl with coefficients yn with coefficients in K. So alpha is equal to summation j goes from 1 to n beta j yj for some elements beta 1 beta n in the intermediate field K. Okay, but now this beta 1, beta 2, beta 3 and so on, these are all elements of K. So we can expand them in terms of this basis x1, x2, xm of F. So we have beta j is of the form I goes from 1 to m gamma ij xi for gamma I 1j gamma mj in, and these are going to be elements of F. And just because x1, x2, xm is a basis for K. And so now combining these, you can write summation j goes from 1 to n, summation I goes from 1 to m, gamma ij xi yj. And so this set xi yj spans L as a vector space over F. It remains to prove linear independence. So now for linear independence, suppose we have scalars gamma ij 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to n. These are elements of F, the smallest field here, such that summation gamma ij, I goes from 1 to m, j goes from 1 to n, gamma ij xi yj is equal to 0. We need to show that each of the gamma ij's is equal to 0. So now firstly, so just to recall, we have L, and then that's sitting over K, and that's sitting over F. Okay, so firstly we will use the fact that the y1, y2 up to yn are linearly independent over over K. So this sum can be written as summation j goes from 1 to n, and then we have gamma, let's write it like this, summation gamma ij xi, and then over yj. So what we have is this sum is equal to 0. And where do these elements live? Well, these gamma ij's live in F, and these yj's live in K. So this thing lives in F, and so these are in F, and this is a basis of L over K. So since this is a basis of L over K, this implies that summation j goes from 1 to n, gamma ij xi is equal to 0 for every I between 1 and m. But that because the x1, x2, xn form a basis of K over F, that would mean that each of these gamma ij's is also equal to 0. Just from the linear independence of the xi's. So this step is by the linear independence of y1, yn, and this step is the linear independence of, and the linear independence y1, yn over K, and this is of x1, xm over F. And that completes the proof. In the statement of this theorem, nowhere did I mention that the degree of L over K is finite or the degree of K over F is finite. But in the proof, I assume the degree of L over K is finite and the degree of K over F is finite. But this theorem actually holds in general, even if the degree of L over F is infinite, or the degree of L over K is infinite, or the degree of K over F is infinite. So a product of infinity and any finite number is to be taken as infinity, and the product of infinity and infinity is of course taken to be infinity. And the same proof goes through, except that instead of finite bases, you may have to take infinite or maybe even uncountable bases, and you would still have this basis of L over F, which would be infinite. And so this theorem also holds in the case of infinite extensions. Now this theorem has some very, it's a simple theorem, and the proof, as you saw, was not very difficult, but it has some very interesting consequences. So one is, so let's suppose that we have an extension, let's just call it K over F, and we have alpha here, and the index of K over F is finite. Okay, so if it's infinite, this really won't say anything. Then what we know is that the index of F alpha over F is going to divide the index of K over F. So this is a theorem. Why? Well, because the index of K over F is just the index of K over F alpha times the index of F alpha over F. So the index of F alpha over F better divide the index of K over F. A very surprising consequence of this is the following, that if the index of K over F is a prime, and alpha belongs to K but is not in F, then F alpha must be equal to K. Because F alpha is clearly larger than K, so the degree of F alpha over F would be some divisor of P, but the only divisor of P are P and 1 itself. The index cannot be 1 because F alpha is larger, strictly larger than K, so it has to be P. It's also kind of useful in analyzing certain extensions. Let's look at an example. So let's take work over the rational numbers. So let's take alpha to be cube root of 2 and beta to be 4th root of 5, for example. Then we know that q alpha over q, this has degree, this should have degree 3 because alpha satisfies the polynomial t cubed minus 2 equals 0, which is of degree 3, and this is irreducible over q. And we also know that q beta over q is 4 because beta satisfies the polynomial t to the power 4 minus 5. So this means that alpha cannot lie in q beta, because if alpha was in q beta, then q alpha would be a subfield of q beta and its degree would divide the degree of q beta, but 3 does not divide 4. So we can say since 3 does not divide 4, and similarly beta does not belong to q alpha. Maybe I should just write q, the standard notation, round brackets, beta does not belong to q alpha, since 4 does not divide 3, of course. Right? And what can we say about the field generated by both the elements q alpha, q beta? So we know that q alpha, so we have this field generated by q alpha beta. It contains the field q alpha, it also contains the field q beta, and they both contain the field q. So this is it's called a diamond of fields. And so what we know is that the degree of this, so here the degree is 3, here the degree is 4. So the degree of Q alpha beta over Q is divisible by 3 and 4. And by 4. Hence, it is divisible by 12. Okay, but we also know that the degree of Q alpha beta over Q beta, this has to be less than or equal to 3, because alpha satisfies the equation t cubed minus 2, which is an equation with coefficients in Q, but it's also an equation with coefficients in Q beta. So alpha satisfies a polynomial of degree 3 over Q beta, and so its irreducible polynomial must be of degree less than or equal to 3. So we know that the degree of Q alpha beta over Q beta is less than or equal to 3. Similarly, you could argue that the degree over here must be less than or equal to 4. And so what we get is Q alpha beta over Q is less than or equal to 12 times, is less than or equal to 12, 4 into 3, which means that since we know that it's divisible by 12, it has to be exactly 12.